Hello everybody, my name is eMoney at SID. Welcome back. Today we're going to finish the second half of Chapter 1. In this session, we're going to cover topics like atomic orbitals, what are they and how to fill them. We'll talk about valence bond theory, and here we're going to introduce sigma and pi bonds. And we're going to follow this with a brief mention of molecular orbital theory, just for the sake of conversing about a theory that is a little more powerful and preferred than valence bond theory without getting into it too much because it's a little bit complicated and outside the scope of what we need to know now. Understanding and focusing on valence bond theory for now is perfectly enough for this course. And lastly, we will get to the juice of this session, which is hybridized atomic orbitals. Now, there is quite a bit written here, and I do not want you to worry all too much about the exact verbiage yet because we're going to come back to this, but know this as a starting place for our discussion today. Atomic orbitals will describe probable regions of electrons around an atom. This probable region is given a shape, and this gives us our very familiar idea of orbitals. Orbitals are important because they determine the distribution of electrons in atoms, which in turn determines the electronic and reactive properties of these atoms. Now, valence bond theory and molecular orbital theory are used to explain chemical bonding, which entails the way sharing and overlap of electrons happen between two atoms. There are limitations to valence bond theory in describing bonding, and the solution to these limitations, or one of these solutions to these limitations of valence bond theory, is a mathematical procedure that's going to mix atomic orbitals into new hybrid orbitals. And this is going to give us our Sp3, our Sp2, and our Sp orbitals. They are based off of quantum mechanical formalism, and we're not going to get into all the math here. In organic chemistry, you probably will if you take physical chemistry or quantum mechanics, but for now we're just going to talk about the concept so we can understand where these hybridized atomic orbitals come from. Now, let's elaborate on all of this. What you have covered or have probably learned so far in your physics courses falls probably under the category of classical Newtonian mechanics, which is going to describe macroscopic objects using mathematical techniques like your kinematic equations, your force equations, and things like that to get an affirmative answer. But the world on the atomic and subatomic scale don't really follow these rules. There were discrepancies between certain theories and experimental results before quantum theory. From these discrepancies spun a discovery by Louis de Broglie in 1924-1925, where he proposed that electrons and other subatomic particles have both wave and particle properties and behaviors. This wave-particle duality is seen in through interference patterns, and this was the emergence of quantum mechanics. This field, quantum mechanics, is heavily based in mathematics, and this is where we get our descriptions of atomic orbitals from. We're not going to be doing any math, but let's kind of conceptually understand where everything comes from in terms of our description for atomic orbitals. Now, this equation that you see right here, all right, it's called a wave equation. It's Schrodinger's equation, and what it does is it describes behavior of electrons or particles in general. So it describes the behavior of particles. And this term specifically, the potential energy term, depends on what kind of particle you're talking about. Is it a free particle? Is it bound? Yada, yada, yada. And essentially what you want to do is you want to solve the wave equation, and what you get as a solution is called a wave function. So wave functions are solutions to the wave equation. From these solutions, you can learn a lot of things like the allowed energy levels and things of that nature. Now, the absolute square of the wave function is going to give you the probability of finding an electron in a location. And a 3D plot of this is going to generate an image of the atomic orbitals. So this is an s orbital. You'll generate p orbitals, d orbitals this way. And this is where we get our description of atomic orbitals. Now, just to reiterate, an orbital is a region of space that can be occupied by an electron. And the energy of an electron depends on the type of orbital that it occupies. In other words, an orbital is a region of space that can be occupied by an electron. A cloud of electron density is a really good way of thinking about it. And here you see a 1s orbital, a 2s orbital, and your 3 2p orbitals. Now, how do we appropriately fill the atomic orbitals with electrons for atoms? The order in which orbitals are filled by electrons is important, and it's determined by 3 simple principles. You have your off-bow principle that states that the lowest energy orbital is going to be filled first. Then you have your Pauli exclusion principle, which is going to say that each orbital can accommodate a maximum of 2 electrons that have opposite spin. And Hund's rule says 1 electron is placed in each degenerate orbital first before electrons are paired up. So let's do an example that's going to help us restate all these 3 principles. Let's write out the electron configuration for carbon and then try to draw the orbital. So carbon is right here. All right, we've done the electron configuration for carbon already in the previous video. So let's write this out. Carbon has an electron configuration of 1s2, 2s2, 2p2. Right, and let's draw these orbitals in increasing energy, right? Your 1s is going to be lowest, then your 2s, and then you have 3 2p orbitals. You have your 2px, 2py, and 2pz. So here are your p orbitals, your 2p orbitals. Awesome. So remember, first rule, Aufbau's principle states that the lowest energy orbital is going to be filled first. So this is your lowest energy orbital. And so it's going to be filled first. And so we put our 2 electrons here. 1, 2. Right, because we have 2 electrons in our 1s orbital. This also reaffirms Pauli's exclusion principle, right? 2 electrons max per orbital, right? We can't be squishing in any more in there. Awesome. Then our next highest energy orbital is our 2s. We're going to go ahead and we're going to fill that up with 2 as well. And then in our 2p orbitals, we have 2 electrons to place. Now, Hund's principle comes into place now. Hund's principle says you place 1 in each of these first, in these degenerate orbitals. These 2px, 2py, and 2pz are degenerate because they are all at the same energy. What you have to do is place 1 electron in each before you double up. So we're going to put 1 electron in here and then 1 here. And that's it. We did not put both of them in the same orbital. No, we want to do 1 at a time before we start doubling up. That's what Hund's rule states. All right, so this is how you're going to fill up your atomic orbitals based off of these 3 simple principles. Awesome. So now we understand atomic orbitals. They describe electron density of an atom. Valence bond theory describes what happens when atomic orbitals overlap. All right, so we know that each atom has atomic orbitals. What happens when 2 atoms try to form a bond? What do their atomic orbitals now look like after the overlap, after covalent bonding, for example? Well, remember, electrons are not only just particles, but they also behave as waves, right? Wave-particle duality. So if one electron's wave looks like this and another electron's wave look like this, and they're both in the same phase, then they're going to react constructively. Constructive interference is going to happen. And as a consequence of constructive interference, the interaction of the 2 electrons in the same wave is going to produce a wave with a larger amplitude. So it's going to produce a wave with larger amplitude. All right, and this is sort of the definition of covalent bonding. All right, bonds result from constructive interference. All right, now destructive interference occurs when the two electrons, the two waves of the electrons, are not in the same phase, and so instead they interfere destructively, and what that creates is a wave with a node. All right, so this is really important. According to valence bond theory, a bond is simply the sharing of electron density between two atoms as a result of the constructive interference of their atomic orbitals. This is very important. We're going to draw a box around this statement. All right, now, when you have two atoms that are single bonded to each other, all right, like a carbon single bonded to a carbon, all right, what you have here is a sigma bond. All single bonds are sigma bonds. So what that means is this bond is formed via the overlap of the carbon's s orbital and the other carbon's s orbital. So there are two s orbitals, they overlap, all right, to create this single bond. Now, double bonds consist of one sigma bond and one pi bond. Pi bonds are the overlap of two p orbitals, a p orbital from one carbon and the p orbital from another carbon if we're looking at a carbon double bond. A carbon double bond, all right, it's the s orbital and the p orbital of one carbon overlapped with the s orbital and the p orbital of another carbon. All right, now what about carbon triple bonds? Carbon triple bonds, or any triple bond, all right, triple bonds consist of one sigma bond and two pi bonds. So this triple bond for this carbon that's participating there, that's one s orbital overlap and two p's, and the same, that's what's creating that triple bond. The s and p orbital of one carbon is overlapping with the other carbon's s and two p orbitals. All right, so that's what defines a single bond, a double bond, and a triple bond in terms of the presence of sigma and pi bonds. Now, with that information, we want to go ahead and talk about how valence bond theory, we said this earlier, is used to talk about covalent bonding, but it has some limitations. All right, so I want to kind of show you this limitation, and we're going to reach where the limitations of valence bond theory comes from, and then how we're going to solve it. All right, so we're going to go ahead, we're going to take our good old carbon, right? We've been talking a lot about carbon. Here's the electron configuration of carbon. All right, and we drew out the atomic orbitals for carbon, and we filled them up appropriately, right? 1s has 2 electrons, 2s has 2 electrons, and then we filled up 1 electron in each of these 2 p orbitals. Beautiful. All right, now what do we know about single electrons, right? They're not paired up. Okay, what we know is that they're probably wanting to form a bond with something else so that there could be 2 electrons. And so looking at the atomic orbital of carbon, we see 2 unpaired electrons, and just looking at that, we would assume that carbon would form only 2 bonds to satisfy the fact that it has 2 unpaired electrons. But we know that carbon's actually tetravalent. What we actually see is that carbon usually forms 4 bonds. So how do we make use of this? How do we begin to interpret that appropriately? And this is where the idea of hybridization and hybridized atomic orbitals come into place to fix this limitation. All right, hybridization is actually a mathematical procedure that is used to arrive at a satisfactory description of the observed bonding, right? We assumed, based off of the way that we drew the atomic orbitals of carbon, that there's only 2 unpaired electrons, so it would only form 2 bonds. Carbon would only form 2 bonds to satisfy its 2 unpaired electrons. But that's not the case. Carbon actually forms 4 bonds, right? So we're going to begin to understand how hybridization comes into place and what hybridized atomic orbitals look like for single bonds, double bonds, and triple bonds. And we're going to start off here with methane. right? Methane is just carbon single bonded to 4 different hydrogens, right? Now, how do we make use of this? How do we begin to understand this, considering that there's only 2 unpaired electrons in carbon? Well, the only way to explain this is if the 2s orbital of carbon, this, and the 3 2p orbitals, 1, 2, and 3, are fused to form these new Sp3 hybrid orbitals with lower energy. So look at over here. Here's our 2s orbital, and here's our 3 2p orbitals. We're going to take these, and we're going to fuse them together, all right? So fuse them together somehow, throw in like a Yu-Gi-Oh! Polymerization card here, and boom, we now have 4 degenerate Sp3 orbitals. We fused our 2s and our 2p orbitals, and now we have something new. We have these 4 Sp3 orbitals, and look at that. We placed each one of these electrons now in a single orbital, and now there's 4 unpaired electrons in carbon. Now there's 4 unpaired electrons that are ready to bind, ready to form bonds, all right, and pair those unpaired electrons up. So that makes sense, right? Because now carbon can form those 4 bonds to hydrogen, and we can explain why methane is the way that it is, all right? So Sp3 orbitals is the hybridization for carbon here in methane. All right, so whenever you see carbon and there's 4 different things bonded to it, when there's single bonds, all right, when there's single bonds around carbon, only single bonds, all right, then that carbon is considered to be Sp3 hybridized. All right, so what's forming these bonds? All right, well, the orbital that's participating from the carbon is always going to be Sp3 then, in that case. Now, the obvious next question is, what if there's a double bond? What if carbon has a double bond? One double bond, all right? How do we understand that? How do we begin to understand that? Well, the only way to explain this is, well, let's refer back to what we know a double bond consists of. A double bond is 1 sigma and 1 pi bond, all right? And a pi bond, which is a staple of a double bond. A pi bond is the overlap of this carbon's p orbital with this other atom's p orbital. All right, this double bond partially is formed by the overlap of a p orbital. So now, if we want to explain double bonds in terms of hybridized atomic orbitals, we want to form new hybrid orbitals, but this time we're going to leave out one of the p orbitals. We're not going to touch it. Instead, we're going to fuse together the 2s orbital with only 2 of the 2p orbitals. What we get now are 3 degenerate sp2 orbitals, and we preserve just one of the 2p orbitals. All right, this is going to explain that double bond. What this double bond now looks like is, well, first of all, it's the p orbitals are preserved. All right, the p orbital of the carbon is preserved, so you have the p orbital overlap. But then the other part of the double bond is no longer just s orbitals, like we talked about previously, but it's actually the sp2 hybridized orbital that is participating in the double bond. All right, and then whatever else is bonded to the carbon here, like look at this carbon and hydrogen, well, the contribution of the orbital from carbon is now an sp2 orbital. All right, because that carbon that's participating in the double bond is a hybridized sp2 orbital. All right, now, again, what about triple bonds? How do we make sense of that? Well, again, remember, triple bonds are 1 sigma bond and 2 pi bonds. That means that the p orbital from this carbon and the other p orbital that this carbon has are going to be both participating in bonding with the other 2 p orbitals from this other atom, this other carbon, right? So in regards to hybridization, we want to make sure we don't touch 2 of the 2p orbitals. So those 2p orbitals, they're going to stay put. They're not going to participate in the hybridization. Instead, we're just going to take the 2s and one of the 2p, and we're going to hybridize them, and what we get are two degenerate sp orbitals. So both of these 2p orbitals, they stay the same. They're participating in the triple bond. All right, but now we have an sp orbital also participating in that triple bond. All right, so this hybridization that we're doing, the atomic hybridization of orbitals, okay, there's a lot of mathematical formalism that goes into explaining this, mathematical proofs of why this is the case. But conceptually, this is the way that we explain, all right, why carbon, for example, is forming actually 4 bonds, even though when we draw out the atomic orbitals for carbon, there's only 2 unpaired electrons. And so you would assume that that carbon would only participate in 2 bonds, but that's not what we experimentally see. All right, and so this is the explanation for that observation. All right, so I'm going to summarize this really quickly for us. All right, when there are single bonds, all right, all right, we're talking about sp3 hybridization. Okay, if, for example, you see a carbon with 4 groups around it, right, 4 single bonds, that carbon is sp3 hybridized. All right, now if you see double bond, all right, if a carbon has 1 double bond, all right, and the others are single bonds, if it has essentially 3 groups around it, all right, then we're talking about that carbon being sp2 hybridized. And if we see some atom with triple bond, all right, and then just a triple bond, then we're talking about that atom being sp hybridized. All right, and we're going to do a few examples in a minute to really reaffirm what we've just learned about this. Okay, so just to summarize, so far conceptually what we've talked about atomic orbitals and how they describe where an electron is likely to be found in an atom. This gives rise to our orbitals, our s, p, d, f orbitals. And we also learned the 3 principles of how to fill orbitals properly. Our Pauli exclusion, our off-bow principle, and our Hund's rule are all used to help us fill atomic orbitals for atoms appropriately. Then we talked about valence bond theory and how it's used to describe chemical bonding. What happens to orbitals during bonding? And we defined sigma and pi bonds. We said molecular orbital theory is a much more advanced description of chemical bonding, but we don't want to get into that because it's a little too advanced. And instead, we talked about the limitation of valence bond theory and how we're going to fix it, which is through hybridized atomic orbitals, right? Some atoms' bonding abilities, like carbon's, doesn't make sense, right? You would think carbon would only form 2 bonds, but we observe carbon to form 4 bonds. We observe carbon to be tetravalent. So how do we make sense of that? Well, we make sense of that through our solution of hybridized atomic orbitals. Our solution is to mix atomic orbitals to form energetically favorable hybridized orbitals, and those are what participate in chemical bonding for certain atoms. For carbon, for example, carbon is sp3, sp2, or sp hybridized, depending on whether it's single, double, or triple bonded. All right, so now we want to do a couple of examples. All right, this first example says identify the electron configuration for the following ion: a nitrogen atom with a positive charge. All right, cool. Let's write the electron configuration for nitrogen, a neutral nitrogen. Nitrogen is usually right here, right? And so that means it's 1s2, 2s2, 2p3. All right, so that is the electron configuration for a neutral nitrogen. 1s2, 2s2, 2p3. Now, what if that nitrogen has a positive charge, an N+? That means it lost an electron. That's why it's positive. And so what we want to do is take off that electron from the highest energy orbital. So instead of 2p3, a nitrogen with a positive charge is actually going to be 2p2. And so the whole electron configuration for a nitrogen with a positive charge is 1s2, 2s2, 2p2. And we can go ahead and fill up the atomic orbitals for that. We're going to put 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then 2 electrons in the 2p orbital. 1 in the 2px and 1 in the 2py orbital. There is nothing in 2pz because there's only 2 electrons in the 2p orbitals. All right, and that's how you would do that. Now, in this next question, we want to consider the structure of formaldehyde. All right, we're going to answer 3 questions about this structure, this formaldehyde right here. We want to identify the type of bonds that form this carbon-oxygen double bond. Well, we know a double bond is comprised of 1 sigma bond and 1 pi bond. All right, so that's a pretty good answer to this first question, but I just want to dig a little deeper here. Carbon here, let's figure out what kind of hybridization this carbon is. All right, this carbon has a double bond, or in other words, this carbon has 1, 2, 3 groups around it. All right, that means that this carbon is actually Sp2 hybridized, right? With the S, there's a 1 right there that we usually don't write. So that's 1 plus 2, 3, right? Because there's 3 groups around this carbon. This carbon is Sp2 hybridized. Let's write that really big. All right. This oxygen, let's look at this oxygen. How many groups are around this oxygen? Oh, well, this oxygen has a double bond, which is a good hint to what kind of hybridization this oxygen is. But let's count the number of groups around this oxygen. 1, 2, 3. There are 3 groups around this oxygen. This oxygen is also Sp2 hybridized. So now let's take a closer look into this double bond. All right, let's look closer into this double bond. What is the carbon contributing in terms of this double bond? Well, obviously it needs a p orbital. All right, and then the other orbital that's participating in this double bond is the carbon's Sp2 orbital. What about the oxygen? The oxygen obviously has to contribute a p orbital, right? Because that's the definition of a double bond, all right? And then it's contributing an Sp2 orbital as well, all right? So this double bond is comprised of 1 pi bond, the p orbitals, and 1 sigma bond, except in this case, the sigma bond is Sp2, Sp2 orbital overlap between the carbon and the oxygen. All right, that's A. Cool. What about B? Identify the atomic orbitals that form each of the carbon-hydrogen bonds. That's a really good question, right? So we discussed what is the carbon-oxygen, but what about the carbon-hydrogen bonds? Let's take a closer look at the carbon-hydrogen bond. Well, a hydrogen only has 1 electron that resides in the s orbital. So the hydrogen is contributing the s orbital to this sigma bond, to this single bond. The carbon is contributing its Sp2 orbital, right? It no longer has it now has 2 Sp2 hybridized orbitals that are going to be contributing in the sigma bonds here. So the single bond between a carbon and a hydrogen is the overlap of the s orbital from hydrogen and the Sp2 orbital of carbon. Now, the last question asks, what type of atomic orbitals do the lone pairs occupy? The lone pairs, what they're talking about are the ones on oxygen. Those are the only lone pairs present here. What kind of orbital do they sit in? Well, we already talked about how oxygen is Sp2 hybridized. That means the lone pairs are going to sit in an Sp2 orbital. By the way, if we're taking an s orbital and fusing it with p orbitals, right, to get some form of sp orbital, what that looks like is a little bit of both of those orbitals. So they look a little bit like this. This is what an sp orbital looks like. Or whatever numbers here. Usually what they look like. All right, cool. Let's do the last problem of this session. Determine the hybridization state of each carbon atom in the molecule. Let's look at this carbon. It's all single bonds. 4 single bonds. That means this carbon is Sp3 hybridized. This carbon has a double bond. All right, so that means it's going to be Sp2 hybridized. And you can also double check. This carbon has 1, 2, 3 groups around it, right? And then if you add 1 plus 2, that's 3, right? So this carbon is Sp2 hybridized. Same with this carbon. It has a double bond. That means it's Sp2. And for this last carbon, also an Sp2 carbon. I really hope that this session was helpful. Let me know if you have any questions in the comments below. You can find these notes. There's a link in the description box as well as an email if you have questions or you want me to do extra supplementary problem sets, go ahead and send me your questions and I'll compile them, and hopefully if there's enough demand for it, make extra problem sets, set videos to answer all your questions. Other than that, that's it for chapter 1. We're done. Good luck and have a great day.